Good afternoon. Tuesday, late April 2023. Over the past few talks, excuse, excuse me, to my health. Minor gesundheit. Bless me. Those are traditional things to say when someone sneezes, as there's a traditional superstition when someone sneezes, that they're expelling bad spirits from their nose. And it has a certain scientific basis, as for example, they have an infectious disease, and the course of the infection's evolution has developed that it transmits airily, and thus by a sneeze that it induces causes a disease to spread. So lots of traditional superstitions have at least some grain of scientific truth, and many of the usual manners of politeness and kindness that are so retained are of the sorts of usual social mannerisms that among well-socialized people are basically instinctual after in the sense that they become habitual as a matter of being ingrained from early socialization, and that it's just not so unusual to notice when somebody sneezes. But anyways, that said, then what we have been talking about, or what's been being discussed here, is the analysis and methods. And so the first outline was kind of real analysis. What are real numbers according to our standard way? And so there's a careful, self-contained, relatively undisturbed formalization of the standard real analysis, and basically constrained in its definition to fit in one of these 1-hour talks or something like that. And so then the next talk in that kind of approach is about the non-standard analysis, and these are for functions that are not a real function and they have infinitesimals or infinities in them, or that they're the limit of standard functions, and so they have behavior that is so approximated in the limit by these, just like real analysis is built, that functions are built. And then it was discussed the theory where that's actually the primary or central object, that as a primary object of the theory, it's axiomatized to exist. It's basically its properties are non-degenerable, and so that they have certain axiomatic properties, that it's primary. As well, though, it can be that that's non-logical or that it's logical, so it can result that this idea of a continuum is first founded as this line continuum, and that's what results that then for field continuity, that's that second continuity. The first continuity is this Aristotle's continuum, and second continuity is this Cauchy-Dedekind continuum, the complete ordered field, or eudoxuses. Aristotle was an ancient Greek, eudoxus was an ancient Greek. Then with regards to this third form of continuity, which is called signal continuity, it's as if after a resultant signal construction, which is when you have a wave, how many samples, discrete samples, must occur of that wave to make it so that the entire information content of the wave can be reproduced. It's called signal reconstruction. It's basically twice the frequency of the highest frequency component in the signal or wave. So the idea is then that this third definition of continuity, or signal continuity, it reflects the Dirichlet problem and the Dirichlet function we've been talking about, that it's everywhere dense, these numbers, but they're everywhere discontinuous, that there's always in any neighborhood a gap, as well as that there's always in any neighborhood a neighbor in this overall space that they occupy, this long line, this line of real numbers, as of Hardy's points of geometry and real numbers together. And so the idea is that from one of these sets that's so dense, then its complement basically reflects that those two together provide this notion of the frequency component, that there's something that occurs already so often that for the first, it's like the lines, and this is mostly reduced to a unit line segments definition, although the complete ordered field is after the definition of all the laws of arithmetic. This line continuity arises without necessarily all the apparatus. And then the signal continuity sort of arises as after that sort of apparatus, or as from the perspective that there already exists one or the other of these other definitions of continuity. then how it results is that basically from any one of these definitions of continuity, you can arrive at structures that are unavailable to it from induction as completed or closed, because it's as of a point at infinity. And so then when you try to model that as according to infinite processes, it ends up that each of these arithmetics and algebras that build these systems must have infinite values in them because these other things exist. And this can help a lot when you arrive at a number system and it's necessary to have infinite and infinitesimal values in it, because to be complete it's so, that then it also works out that they are complete and so. And then it helps to arrive at how to solve these middle and nowhere problems, where we know it goes off to infinity, and out of infinity it comes back. It must meet in the middle. And this is, again, a sort of sandwich theorem, or for Dirichlet, the pigeonhole theorem, put together, that make it so that it's possible to have a much richer and more cogent mathematics, though that it does demand that it's not taken out of context what could otherwise be wrong inferences. And it takes a little bit more care in the disambiguation and specification of these objects that admit these otherwise equalities under extensionality, about how to imply that they imply infinite processes with respect to each other, also called a super task, which is something that has actually infinitely many steps, and then the idea is what is the value at that step. And this is usually familiar to dynamical modeling as what's called x sub infinity, or x is t goes to infinity. That these are the kinds of ways to make from analysis and methods that at least there are these replete definitions, where replete means complete and complete again in full, of what are each of these in their closed domains, their complete definitions, which are, though, incomplete, for example, as Gödel can prove, so that Gödel always opens any of these theories strong enough to model the object's arithmetic, being the integers, each of which is, as the relations are so established for constant monotone increasing, strictly increasing, or regularity and uniformity of the modular, either way, which can implement the integers. That then altogether they arrive at this it's three-legged stool, while the unicycle of standard real analysis, once you get used to how to write it and gain your balance and keep the balance of things, of course, still is a perfectly simple way to get around. A tricycle is a lot easier way to not fall off, in the sense that it stays standing when you walk away from it. So with that said, then there's these three definitions of continuity that can be defined in terms of each other, that it's most simple to define it either from the signal side, although it's kind of the last thing after mathematical developments, otherwise it can be arrived at, and most easy to arrive at it from the Aristotle side, because of all of Zeno's arguments and all the most usual mathematical paradoxes that anybody ever first heard about, which are the paradoxes of motion and continuous uniform motion. That results from the development of this line continuity, that field continuity is great because it's got algebra and arithmetic all put together in the middle, and it's standard and it's linear, and the inequalities always fall one way, and so it results that it's very neat to do most mathematics. There's nothing wrong with it. That for this wider context of mathematics, that there's more available of these objects after intuition that are formalized, that are made for rigor, that have proofs that establish why they're so that it can be arrived at how these things are arrived at from the simplest, least first principles, called axiomless natural deduction, which makes it so that there really is a distinct and unique numbers in geometry. And then that is, well, when we think of that and our place in the universe, which exists abstractly of us, we are the figments, that is objective, that is Platonist, that is strong Platonist, that we can still, each of us, have our own theories of everything about it, or lack thereof. Everyone can still have their own multiple universe hypotheses. There are hypotheses, any one of which may be so contrived with respect to then whatever so ones are true, either between a shared interpretation with somebody else, the story, or true as in all of science will back it up, and that the scientific method and the culture of science and the history of science and the data of science and the reproducibility of science make that so a very strong truth for anybody. And that in that one, it also has to result from a theory that's true. So these are the kinds of things that arrive for these analysis and methods, why it's better to know enough about these thinkings that went into the linear curriculum from what was finally selected as the standard way, as a round it holds it all together. And so then in the previous talk there was this discussion of why there's this line continuity and signal continuity and how that fits with a standard, because a standard needs to be adjusted, if only so much, but thoroughly so that it fits together and does not have a contradiction. That there's no resulting paradoxes in this sort of non-standard development. It's an extra standard development, not an anti-standard development. And so these are the kinds of things that I find most interesting and compelling about continuity and discreteness, or the analog and digital, or the particle and wave duality and this kind of thing, because it checks all the boxes, and that goes a long way. So getting into that, then there was some discussion of, for example, functions that are non-standard functions that for all finite inputs are one thing, and we expect that to have in the limit that same value. In fact, that is our very definition of limit, that a case for induction is built and something grows closer and closer to its limit and never gets farther and farther away. And so for some, that's the limit that it can only approach the limit from one side. For example, if you imagine a value that slowly but steadily rises from 1 to 2, and its limit is 2. Or if you consider the sum of the inverse powers of 2, 1/2, and then 3/4, and 7/8, and 15/16, and that its limit is 1. And then there's also a notion, imagine a curve like the sine curve that has absolutely regular periodic motion over time. So that in any given multiple of its frequency, you know that is the same, any given multiple of its period, you know that is the same as at 0. Now, it's not said that has a limit because it oscillates. Yet if you take that function divided by x, it also oscillates. It'll always go above and below its limit for all time. So for a long time, just like functions were only what today we only call classical functions, which the definition has expanded. It's just an example that there's a definition of the limit that's expanded to support that this function called complementary sine, which is sine x divided by x, has a limit and it's 0, because it's the same as 1 over x has a limit and it's 0. And you can aver that any function that is not a higher order than 1 in x divided by x as x goes to infinity, 0. So anyways, these non-standard functions that belie their finite inputs are exactly as about this equivalency function, or that we have a function that goes from 0 to 1. We didn't start saying that the function has values that go off from 0 and go somewhere. We said that we have a function that goes from 0 to 1, and then that's just split up infinitely many times, and then the limit still goes from 0 to 1. It's called a continuum limit. It's called a limit of standard functions. It's called modeling a function by standard real functions. It arrives that it's not a real function. Here it's not a real function because it has infinitesimals all between 0 and 1, and there are no points between them, but they still satisfy being a continuous domain. And it's countable, but it's not a Cartesian function. A Cartesian function can have its elements reordered. This may not. It simply would destroy its definition as of this limit. This definition of modeling this function so simply as a limit of standard functions keeps it real. And it keeps it real. So this is the kind of things that go into the non-standard analysis, and examples of functions that are not the same for their finite inputs as they are in the infinite. That x sub infinity of this function equals 1, regardless of what order it's been approached at. And also it's kind of neat that it's just, you just divide a unit into however many pieces you want that are constant, monotone, strictly increasing, their differences. And it's just like the fractions. It's just like the fractions as they go to 1 over infinity, but it still stays going from 0 to 1. So it looks like 0 all the way out to infinity, but really that's just infinitesimals, because those standardly looks like 0, but really it's 1 iota, 2 iota, 3 iota, off to infinity iota, these iota values. It has a perfect mathematical construction and is rigorous and in its own way well-founded. And again, that's defining it the standard way, defining it as the limit of the standard as was just described. That in the impasse, it's not arrived at via induction, it's arrived at via deduction and then induction. So then that it's also central and primary in a theory by itself, or line drawing the act, has that it falls down from also being the spiral space filling curve. Well, what's that? Well, it's kind of like if you draw a line, so it goes from point to point to the end point. They're contiguous, they're connected, and you can only put down the pencil and draw and then lift the pencil. There's only one act of it. And then it's a fate, it's an opus, an act. That the spiral space filling curve is so simple. It's like, well, every time you draw and make a point, and it's like scribbling a dot on a piece of paper, if you can always maintain going outward. Because the only idea that it has is that it constantly goes outward and constantly increases in dimension. So it's a point at 0, and a point next to it in dimension 1, and a point next to it and to 0 in dimension 2. And it goes all the way out till it draws a circle through all the dimensions. Or you can just go through 1 or 2 dimensions. It exists in any number of dimensions. It's a spiral space-filling curve, a hyperspace of any number of dimensions. Euclidean, real. So anyways, this spiral space-filling curve basically represents that it's just an abstraction of continuity. And one person to point to for that is Brouwer, L.E.G. Brouwer, Lutwidge Brouwer. And so in the 1920s, when regular ordinary set theories come along, he had some strong objections. And so did Poincaré, and so did Hausdorff, and so did Vitali, and and so does Skolem, and so does Levy. And so the spiral space filling curve is an example of something like a continuum that Brouwer has, though his just kind of clumps and divides. His seems more like the idea of multicellular reproduction. The cell divides, and they divide, and they divide, and they divide. And this is more that this active line drawing basically results in this one dimension, this restricting the spiral space filling curve to one dimension. It's this line drawing. And in 2 dimensions, it's filling in a dot, just like it is on pencil and paper. A space filling curve, meaning there's never any gap left in it, that each point is next to each point, and then it's just, it fills the space, that there's only some necessary properties that each point in the line is both as close to the origin as it can be, but no closer than any other point. And that it also, there's a straight line that so results through it, and so that the next point on that same straight line is connected to it, but beyond it. And none of these shells of the spiral are, except in the infinite case, anything but a neighborhood of shells about the origin, infinitely dense and continuous in all these neighborhoods, that's built up after this line continuity for this line continuity. So then this infinite spiral space filling curve ends up being complementary as to this line drawing in one dimension, which results a line segment. Or, for example, that is pieces at any given radius from this curve makes a circle. And there's that, in any given number of dimensions, they're basically an orthogonal basis. So this is a primary and central notion that reflects a non-standard approach to space, Euclidean. And then what results is it so provides this orthogonality in straight lines in a circle, or the objects of classical constructions as features. is then this axiom natural deduction arrives at this axiomless geometry, which from a point makes the space, or from the space makes a point, either way, the inward spiral. But here the outward spiral, that this spiral, space-filling curve, is a central and important and primary object of mathematics. And that it's non-standard because used incorrectly or without maintaining that the function theory is kept together about the Cartesian and non-Cartesian, and that otherwise that the closures of arithmetic and algebra have to take into account their field operations and their closures. We'll get to that in a second. That otherwise, then it results for this axiomless geometry, Euclid's geometry just arises from it. You can just say that Euclid has just picked certain particular structures out of this space, and we can build them with these same sorts of tools. And so the axioms that he provides, that Euclid, the panel, but that Euclid provides, just result being derived from this. And thus then that as any of those axioms like the parallel postulate hold or don't hold, this results this axiomless geometry. So for somebody who wants a theory with real numbers and also wants to have the least amount of baggage, it's free. It then results that it's very compelling, beautiful, and strong, which have that it's independent of anything that any person needs to do for it. It's strong. So in terms of then these discussions, we talked about standard real analysis just to make sure that there's a full complement and a good definition of the course of standard real analysis, because we wouldn't want people then to think that they have to take weaknesses out of that to accomplish these limits and the other things, because the existence of a differentiable region by raw differentials basically breaks standard real analysis. In the path integral discussions we're talking about, because formally and fundamentally it would map to that same object, and without changing the theory of functions it would break. And so the illative, or which is a way to make it elated of sorts, that the univalency holds to make for that kind of object that's applied in some theories like commodity type theory, are considered an improper class set distinction. And similarly, the Dirichlet problem, where it's the rationals are countable, but this would be huge, is solved the same way. Paradoxes are not to be put off. Paradoxes cannot be axiomatized away. Inference is free and deduction is free, and if you can ever make a paradox, it's true, and it proves a paradox and contradiction, and then anything can be broken with it as a rule. And so that otherwise this disambiguation to resolve the things is necessary, because mathematics deserves it, and it has one already, and it's a disservice not to observe that, because it would be dishonest. And the last thing that anybody needs in terms of the objective and abstract and critical and reality is fallacy or lies. So it was discussed that, and then how that is so that these sorts of processes or functions are real. And then there's various names for these things, like R is, yes, a set of complete real numbers. In fact, for some people, then R is a label, a letter for a set of real numbers. And all that's important then is that it's so defined that for all the formulas and theorems about the elements of R as a set hold true. And so that's one key thing about that. Well, for this continuous domain, we'll call it, say, R dots or R bar. Whether R dots or R bar is the field or the line integral is a matter of convention. But let's say that the line integral is R dots and the field is R bar. But really, it's almost more so that the line integral is R bar, which is R with the line over it, and the field is R dots with the dots over it, or an angle or something like that. Hat. The idea then is that as long as the same formulas so arrive, and for real analysis, that's the intermediate value theorem, because from that you can derive the fundamental theorem of the integral and the fundamental theorem of the derivative are set up. Then after that, because only those properties are required, then it becomes that they have a very compatible system. They're not interchangeable, these sets of elements. They're different, entirely different kinds of objects. But in the space of real values, they just happen to so share by their replete definitions that any of these definitions of continuity by itself is enough to establish all the properties of the space and in geometries. And then it is built about these others coherently and carefully, so that it can be non-contradictorily. So these kinds of things going on. So those were the talks of the first few talks, and then there was something along the lines of talking about the factorial exponential infinity identity. And what this is that when you think about all the zeros and ones, in every way that a sequence can be zeros and ones, we were talking about things about like the Markov processes and any way to consider a sequence of zeros and ones, that it has a beginning, and then an infinite sequence identified each by a natural integer. So this is infinite and unbounded, say. We're not claiming also that the box has a bound, because it's unbounded and infinite. That then there's the collection of all these sequences of zeros and ones. And this has a name. It's called Cantor space, for Georg Cantor, who is the main proponent who pulled together a bunch of the results for uncountability of the complete ordered field that is all part of standard real analysis in Cartesian functions. So the idea is that that space establishes also combinatorial concerns. So on the one hand, that Borel makes immeasurable spaces, and these combinatorics make for counting arguments that from looking at just the space in its terms, it's possible to arrive at an expression in terms of the factorial, which is like for factorial 10 or 10 bang, 10 factorial is 10 times 9 times 8 times 7 times dot dot dot. It's the product of numbers from j equals n to 1. And, or 2, for example, because times 1 is trivial and not times 0 because that's vacuous and annihilating. And then the exponential is 2 to the x, 2 to the n. And so the idea is that it was possible to arrive at via a means of this counting arguments and about the space as it is when the space is a square. So in Cantor space, in the uncountable, it's infinitely long. There are infinitely many more members on the list than the list is wide. The square space is basically that, well, it's infinite both ways, about the same. And that any of the members that exist in the space have that it's only so defined, really, the square way, as these values, the zeros that begin and seem to go on forever, but reach to 1. So this list, the square list, has an end. It's got an infinite in the middle, going up and down. So it starts at 0, goes to 1/2. Somewhere in the middle, it's 1/2. And if you happen to split it there, then if you take the following digits, it looks like an exact copy of same box. So it's recursive, it's self-similar, it's fractal. Inside each of the halves is a total copy of the box, the square. But the idea is that it ranges over all these values, and then that when you look at the columns, each column is half ones and half zeros, which is interesting. And then, but each of the rows, then it works out a way to find that half those rows are equidistributed 1 and 0. So this was discussed mostly in the previous talk, just to frame it out a little bit before getting to this point. That otherwise these numbers, factorial and exponential, don't have other known relations to each other in terms of closed forms. It's exist, but you can easily prove it's not so. You can easily prove it's not so, but exists according to the concerns of this space. And then the question is, well, what happens when you plug in numbers? Is the numbers get close. Numbers get close. And they resolve as to given ratios. And so I discovered this in about 2003, and I put it together, and I was quite entertained with it. And then, I found that it was flawed. It can be proven wrong because and besides that, it blows up very quickly for small numbers. But it only ends up true in the infinite case. But plugging in bigger and bigger numbers, they started to fall out. Then, and via some manipulations about the intermediate theorems in the development, that worked out, because then I just dealt with formulas in the formulaic from having framed it out and pulled it back, reformulating the gamma function in terms of a doubling formula and some of these other formulas I found about the gamma function. That I ended up also with some estimates for factorial, which is a closed form for a formula, and you want to compute 10 factorial. Well, you just got to multiply all the digits less than it. Well, you want to compute the factorial of 500 billion, it takes 500 billion steps. But if you have a closed form, it takes less steps, many less steps. So then I discovered that, well, I'm not the first person to have found an approximation for factorial. Although I still have never seen a relation of an identity in the factorial and the exponential before. So I plugged in lots of big numbers to the factorial, and it gets pretty close. It's the same number of digits. Its first couple digits are the same. It gets closer as it gets bigger. It's approximation, the vanishing error term. So that's pretty significant. And if I think about something like Aristotle's continuum and line continuity, that's retroclassical. Addressing that in terms of the uncountable and uncountable is just like resolving, disambiguating formal things so that they no longer disagree, and explain how they work together because they have to live together on the one real number line that is full and everywhere full of real numbers. That then this factorial exponential in identity is much more something that's like, I've never heard anybody even consider or discuss that before. That would be like a formula or something that somebody discovered or invented that was basically a profound advance in mathematics. This other stuff is retroclassical modernization and apologetics about foundations, which is an effort in itself, and it demands a philosophy of science and philosophy of mathematics. This otherwise kind of lies in the realm of the applied that's would almost seem paradoxical. So it's kind of like the Banach-Tarski paradox. What is that, you might ask? Well, Banach and Tarski got together. Banach is of the Banach spaces we've been talking about, or compact linear normed vector space. And Tarski is an algebraist and a logician and studied some things. And so anyway, named from them is this paradox that according to a matter of decomposing things, that you can take and the idea is you can take a sphere or a ball and separate it into three everywhere discontinuous parts, and then via translations and rotations reassemble the two pieces on one side and the two pieces on the other side from these four or maybe five parts, depending on one of them is the pole, according to these arguments, and arrive at two identical duplicates. It's called a doubling space or doubling argument. Now for Vitali, who was before that, then we have that Vitali and Hausdorff made a geometric version of this proof. Then there's a different one called an algebraic approach to this proof, and they're different. They're derived totally differently. And then they don't agree on either side really how they got there. But it's possible to build it on either side, and why it's called a paradox, because it doubles this thing which otherwise are measured according to their spaces. And then some have that's like, well, it was measurable, but then it's not measurable to do it like that, so you could get wrong results, just like if you add up infinitely many finite things, it's infinite, it's not finite anymore. Here the idea is that, well, somehow you have to be able to disassemble these things into non-measurable parts, but when you put them back together, they're measurable again, just because each one so satisfies that they're neighbors. So this is the Banach-Tarski theorem, but who's really interesting about it, from the geometer side, where a geometer is somebody who uses geometry, or a theorist in geometry, is that the Vitali had already made one for the unit line segment. He made it doubling space, and he's like, it's between 1 and 3. I'd say it was 2, but then it would be exact. It's doubling space. So Banach-Tarski paradox is reduced down to this Vitali-Hausdorff revitalization, because Hausdorff was also a very strong geometer and able, for example, to show that all these 0-1 sequences might be uncountably many, but I can make one each, and my rule is, it's there, each one that can be defined results that the countable universe of definition is not having any that don't have a definition. Proof by contradiction, proof by contradiction, proof by contradiction. And so it's called a paradox, but then really it's just kind of, it's just unintuitive without having something to intuit and resolve it, in which case it becomes resolved and just becomes an ansatsa or setup and reflects its preconceived notions, its enthymemes, or these settings with unstated assumptions, and these kinds of things, that it results that it's not a paradox, and also it's part of mathematics, and that its next step then is to be for the applied. So getting back to this factorial exponential identity then, what results for it is that it's Borel versus combinatorics, because it results in the extreme that on the one side the argument is framed about Borel's argument, and then it's almost everywhere one way, but then according to the combinatorics, it's combinatorial enumeration, combinatorics, it's almost everywhere the opposite. Then the idea is to assign how and why it works up, that's the half in the middle, or that otherwise there's this meeting in the middle of nowhere, because it doesn't exist to either side, but neither does other side to each other to the other side, but they both must exist. So this middle of nowhere, a metaphor as I've been putting it, is quite apropos, because then what entails from it is that it will allow that this sort of result is really what will make it so that all kinds of a bunch of different results in what's called the emergent, that after scientific experiments, like we have to multiply the whole thing by 1/2 somewhere because it's coming out twice. Well, it was like as we're at some kind of doubling space, or that there are empirical formulas that besides being emergent as from other notions in the field and notions in the models as of different tendencies and propensities in the physical interpretations, emergence, that this is actually a mathematical emergence of sorts. And so then it works up for these, it makes new laws of large numbers that are the result of working from the space instead of the point, working from the outside instead of the inside, and vice versa. That the inside has an outside and the outside has an inside. There's a middle. And so these are the kinds of things that's one of the things I found most compelling, because I found it as a mathematical relation, and I hadn't really thought it all the way out. It's like, well, disprove it first, and then it's very easy, simple, trivial to disprove. And then I started applying it to all sorts of formulas. And then, for example, recalling the discussion of the limit earlier, there's various tests that one can make for convergence, and for a given particular series in the middle of development, it was shown that, for example, that this series was not convergent. And I took that to heart because it's part of these laws of convergence, and it's relevant. But then when I looked at a neighboring development called Stirling's, Stirling's formula or Stirling's theories, I could apply that argument to Stirling's formulas and break his proof too. So in this manner, how I defended that part of the proof was that Stirling's approximation is known good in the sense that it works and the numbers come out right and it has a proof of why it is. And then, for example, this law about convergence applied to it would imply that it was a contradiction or otherwise wrong, but it's not. And so these are the kinds of things that, as I approached it, then I was able to establish at least this tenuosity that is tenuous between Borel and combinatorics. That's Borel versus combinatorics, but it's Borel vis-a-vis combinatorics. And so, insofar as mathematical developments go, that to me is one of the most enigmatic setups, and I'm going to be turning some attention to it because I've let it sit, and so I can think about it for a long time. And while I went about learning the rest of the way that I could figure out so far of how potential theory works, how the quasi-invariant is set up, these pseudo-differentials, all such matters of these notions of what happened at the ends when there's the degeneracy or things break down, but how they must add it back up, the adiabatic and non-adiabatic, models in physics, models in mathematics, terms about real infinities, non-standard analysis, real what have real domains, the theory of potentials, the dualities of particles and waves. Those are always advising the eventual continuing development of this factorial exponential identity and related numeric terms that follow out of it, for example, finding various closed forms for Stirling numbers or other combinatoric forms, especially in the infinite, which would be symbolic calculators of a sort, real numbers. And there are lots of places now that in the standard world, and especially the widely published world, that there are these higher level approaches that are relevant to these kinds of things because they're higher level approaches to the non-standard from one-legged standard tower compared to this tripos or the three-legged tower, basically, that's able to just grow those together and find how they meet in the middle. That for me, that's very satisfying, and it makes me very happy because it's possible then to take what are these redevelopments in the fundamental, the foundations, the soul foundation, again, which should fail by this metaphor of the tower, but is a thing, that at least this definition of continuity, of the long line continuity, has these three definitions of continuity, and makes for that what would otherwise have been uniqueness theorems or existence theorems of some of these other statements, that then, though it introduces extra bookkeeping and, in a sense, baggage for some of these developments, when introducing other terms, that there needs to be an extra apparatus to accept heterogeneous terms, that these terms as well are at least resolved and not eventually fundamentally paradoxical when, as modeling each other, would simply witness each other false, which would be wrong. So this is something that I imagine that a lot of people, when they try and approach these things, have suffered very greatly in terms of their conscience, their mathematical conscience. This is the idea that the mathematical conscience it's a form of honesty, and it just means that a conscientious mathematician is conscientious 24/7, so they have to be a rigorous formalist, and they can't be a retrofinitist. And then it's their responsibility to figure out how that's not a paradox. So that has made me happy then, because otherwise I'd wonder that pretty much any grad student in the world, if they wanted to be the most famous person they could ever be, they would want to solve continuity, kind of like so. And then about the factorial, exponential, identity, and infinity, for me that's just reflects then, here I kind of frame it in two things. One is about the complete ordered field. The complete ordered field is the real numbers, and then basically it's defined and described according to algebra, not geometry. Geometry and algebra are two different things, though they model each other and they attain to each other. But according to algebra, then there's a way to show that it's unique. And it's unique among all other fields, insofar as then that the complex numbers so form a field, and that they're between the reals and the complex numbers, that those are pretty much the only complete ordered fields, because they're the only objects of mathematics with the operations defined on them that so define such properties that consistently and closedly they implement all the features. So anyway, one time I thought of that in terms of infinity and the limits of these functions, and for between -1 and 1, kind of like the unit interval, but just between -1 and 1, it's also possible to define field operations in terms of the limits of functions, and then it's just an example that it's not unique. It still exists, and it's unique, with the full plane is unique with the full plane, R and C, but a usual theorem taught in abstract algebra classes in college, university classes ends up being non-unique, and that it would rather be called distinct. And so these are the kinds of things that happen when there's a wider world. And now it's similar. Let's see, there was that non-unique and distinct. The definitions of continuity and distinct. Borel versus combinatorics, space, square space, Cartesian and non-Cartesian functions. Anyways, these field operations defined for the unit interval, or the twice unit interval, or the unit positive and negative interval, is an example of something that is real, then again, and attained to by the closures of each of these series, but then comes together like so. And then another idea about the idea is this, that in probability theory, there's the central limit theorem. And it's an incredibly important fixture for all manners of the statistical inference, because basically it has it for a distribution with a mean according to a law of large numbers, that it will look more and more like a normal curve, or the bell curve. That for large populations, the bell curve is perfectly satisfactory to reflect a non-biased centralized distribution with with a variance of sorts that is not skewed or biased. And I have to refresh some of my understanding and make sure I don't misuse those terms, and any mistakes are my own. But the idea is the central limit theorem is sort of a building from the standard and off into its cases according to induction. Well, there's perhaps this complement called this uniformization limit theorem, that things go flat in the infinite, because maybe it's not got a central distribution, or this and that. So this is called the long tail sometimes, that a distribution starts and then it has a significant mean, and then all the long part of the tail is the long tail. Or that's essentially flat. If you think of individuals, and it's like they have the same name as somebody else. Now in some places that would be like centralized. For example, a small town where everybody has the same name, compared to one where it's like nobody has the same name, or numbers, or other random data, as it were, that it varies how that is. Or when you think about records with attributes, if the record has maybe usually one attribute, or you want to have the statistics of the count of attributes. For records with an empty attribute, that might be all the universe of them. But then when you try to figure out how many of those, that would usually be more of a Poisson distribution, okay, which is a bump and then a long tail. whereas the idea of the normal distribution is symmetrical, half are above and half are below the mean, average. So anyways, the idea with this kind of laws of large numbers and the fact that it's not necessarily unique, the extrapolation, because there's an interpolation if you can figure out an opposite end that it would naturally have to fill into. That results that this kind of thing makes for why there are more laws of large numbers than people might know about, and there are alternatives sometimes to what only induction offers and induction only offers. Again, as for a course of deduction and deductive inference. So in the analysis of the methods, this has basically just been a talk about that. A, we already have all the standard analysis and methods. B, now it's extra standard. C, and it includes some of these non-standard applications that are real. So these kinds of things going into what make for solutions of these kinds of things, and helping to figure out how the dynamical modeling can work to explain these kinds of things is a real deal. Now, it's not necessarily sensible, fungible, and tractable, where the idea is that first something has to be sensible and unambiguous and well-defined, well-behaved. Then it has to be fungible in the sense that it works with the other tools of the analysis, the other methods of the analysis. And then it has to be tractable in the sense it has to be able to be applied via, for example, divide and conquer, or parallelized, or that it can be made parametric, that it can so result that via an arithmetization or a geometrization that the methods of arithmetic and geometry can work up and over it. Tractable. These are the kinds of things that at least then would have an intuitive availability vis-a-vis an absolute ban, and the fact that that would be unmathematical. In fact, it can be turned around that things that deny it are simply unmathematical. Not that such a heavy hammer is to be wielded lightly, but it does swing fast. So such sorts of ideas then about how to understand this particle wave duality, well, now we have to figure out atomic molecular chemistry. And there's particle wave duality, and these waves have waves, have waves, have waves, have waves. And make a resonance. And these nonlinear approaches have higher order terms, and then we're working them down in rank and making it so that then we can build out approximations off each one of those, because then we don't have time for those either. And we need to have a computer crunch them down because, by the way, there's not a long enough roll of paper to write this all out. These are the kinds of things then that get into how it can be so easy to fit in a course of a few such discussions. Again, the intuitions, the proviso of analytical and deductive tools and courses of inference, the deductive and the analytic and the inductive, that so result then these sorts of settings are each natural and not alien to each other or étranger, nor against each other. That it becomes Borel vis-a-vis combinatorics, not Borel versus combinatorics, and vice versa. These are the sorts of things that for somebody whose goal is to understand the continuous and discrete, or at least have a pretty firm idea, or for example to know the foundations and be a fundamental theorist, or the digital and analog, or all these other things about how technology works, about how engineering works, about how physics works, and then also for things like the statistics and probability, how it can be assigned that the ubiquitous success of mathematics in modeling systems also results that in many cases it's the only tractable empirical means of doing something, unless you can find 10 million hamsters to run in their wheels to power the hydro dam, or a billion clock cats to look left and right and see if one of them finally caught the dot. These are the kinds of things that go into then, having that somebody who comes out with this sort of thing can say, according to Heraclitus and his dualistic monism, and what results from that in this square of opposition, what makes for this after axiomatization by reflection on principles, these axioms and classical constructive tools, and also this complement of the accoutrement of some Zeno's tools and some line drawing and some basic fundamental conditions for geometry, that then we can have all our full standard analysis and also this extra non-standard analysis that's not anti, it's actually extra. And then we can get into our statistics and modeling of probabilities and figure out for conditional probabilities why it's not just Bayes' world anymore, that it's bigger. And so these are the sorts of things that then would enable when it comes otherwise, is that the clock cat just ended up and it's on the other side. And nobody knows why. Or, boy, those hamster wheels just won't keep coming. Or this and that kind of thing when it comes to otherwise the ubiquitous success of mathematics in all theories and the ubiquitous success of computers and divide and conquer of work after numerical methods and approximations, that it can get a lot more work done with computers by a lot less work done by computers. Though it does involve at least this level of the organization. So yeah, this has been my talk for today pretty much, and as far as this essay, this hopefully learned advance and framed in the context of the discussions that have already been, carries with it some meaning, is that with those such notions, all these books on mathematics make more and better sense. And there's nothing wrong with that. Let's see here. Well, that's what I'll read for today, and then we'll get back into some of this analysis and methods, some more of the ideas. It was a great talk the other day about the circle and the idea about how it's transcendental, whereas from our classical constructions it's unattainable. At the same time, from the other perspective, it's the opposite way. Yet it so results that they're together and grind each other out. That's the thing. And then from the previous discussion about the differential and all the stuff, and quite a few readings in the differential, and then about the nonlinear analysis and the path integral and its developments, including Jordan measure for line continuity, the Dirichlet problem for signal continuity, and then regular mathematics in the middle called the integral, as long as that's standard. Not that the integral can't be implemented in these other models of continuity, but just that as long as we're doing so, we always have delta epsilonics in the standard. Delta epsilonics. We also always have delta epsilonics in the non-standard too, but the point being is that all that's formally defined, rigorous. Except the Jordan measure isn't formally defined because it can't be a measure until it's resolved. And the Dirichlet problem isn't formally defined because there's that, But it's brought together. And so these sorts of things then for all sorts of modern 21st century mathematics as foundations is why it's a lot closer than you might think. And in fact, it's close enough. And it's yours. It's an objective theory. Well, I hope this finds you well and in good health, and to you and yours. Well, since I sneezed, mostly I've just been wheezing, I suppose. But it's conscientious. Well, have a great day. So long.